So what's the point in studying the characteristic polynomial? Well, remember that polynomials have roots. So let's say that lambda is a root of the characteristic polynomial. What does that mean? That means when we plug in t equals lambda into the characteristic polynomial, well, remember, by definition, that's the determinant of lambda times the identity minus a. This has to give us 0 because that's what it means for lambda to be a root. But if we think about this for a moment, what we're doing is we're saying that the determinant of a particular matrix is 0, and that's exactly what it means for that matrix to be singular. So saying that lambda is a root of the characteristic polynomial is the same thing as saying that the characteristic matrix with t equals lambda is a singular matrix. And then we realize that we've seen this before. This is the exact same idea as lambda being an eigenvalue of A. So the punchline is that the roots of the characteristic polynomial are exactly the eigenvalues of our matrix. So how do you find eigenvalues? So if you think about everything we've said about eigenvalues, all we've said is that if I have an eigenvalue, here's some things I can do with it. We haven't said anything about calculating eigenvalues. And so what this is saying is that the roots of the characteristic polynomial are the eigenvalues. And this means if you want to find eigenvalues, you need to find the roots of this polynomial. So let's look at an example. Here, I'm calculating the characteristic polynomial of this 2 by 2 matrix that's filled with all ones. So here I have t times the identity minus a. Well, when I take my appropriate determinant here, I end up with t multiplied by the quantity t minus 2. Well, this is already factored for me, and what I'm finding is that the roots of this characteristic polynomial are 0, so t equals 0, and t equals 2. This means that the eigenvalues of this matrix, so the 2 by 2 matrix where all the entries are equal to 1, are 0 and 2. This is our first eigenvalue calculation. It's very exciting. Here's another example of a 2 by 2. So here we're taking the determinant of the characteristic matrix. Here the matrix we're studying has columns 1, 1, negative 1, 2. So we have t times the identity minus a. When we take our determinant here, we end up with the quadratic polynomial t squared minus 3t plus 3. And I stared at this for a minute and I couldn't factor it in my head. But then I realized that's not a problem because for quadratic polynomials, we have the quadratic formula. So I went ahead and applied the quadratic formula to this quadratic polynomial, and I found the two roots. Lambda 1 is the first root, which is 3 minus root 3i over 2. And lambda 2 is our second root, which is 3 plus root 3i over 2. So we get two roots of our quadratic polynomial. These are the two eigenvalues of our matrix. And one thing to note here is that these eigenvalues are related by conjugation. The conjugate of the first eigenvalue is the second eigenvalue here. So that's interesting to note. So we use the quadratic formula for this 2 by 2 to find the eigenvalues. Here's a more sophisticated example. Here we're looking at a 3 by 3. So here A is this matrix here. We found the characteristic polynomial, and I managed to factor it. So here the characteristic polynomial factors as t plus 2 multiplied by t minus 1 multiplied by t minus 4. Well, here we can figure out the roots. They're negative 2, 1, and 4. So that tells me that the eigenvalues of my matrix are negative 2, 1, and 4. So by finding the roots of the characteristic polynomial, we are finding the eigenvalues of our matrix.